In this video, we're going to talk about some of the properties of definite integrals. The variable of integration in a definite integral is sometimes called a dummy variable, and it's not meaning that it's an unintelligent variable. It just means that it's a stand-in. So think of like a puppet that's called a dummy. This is because it can be replaced by any other variable without changing the value of the integral. So the integral from a to b of t squared plus 3 with respect to t, notice the t's match here, is the same thing as the integral from a to b of x squared plus 3 with respect to x. They have the same value. So that's one property. Another property that can be important is two special integrals that exist, and you can get this from the geometric definition pretty easily. If f is defined at x equals a, then the integral from a to a of f of x dx is going to be equal to 0. So let's think about this. If you are drawing, you've got your graph, and you want to talk about the space between x equals a and x equals a, well, that's the same line, so there's no area there. So it makes sense that it would be equal to 0. And if f is integrable on the interval from a to b, then the integral from b to a of f of x dx is actually the opposite of the integral from a to b of f of x dx. So one trick that WebAssign likes to pull and I like to pull is we put a really complicated integral, but the bounds are the same. So notice you have a 45 and a 45. This is just going to be 0. You don't even have to worry about all that trig. This one illustrates the second property. So I could put a negative sign out front and make this the integral from 0 to 2, okay, of x with respect to x. So that means that f of x would be x. So basically we've got this line out here, and we're going from 0 to 2. So this is the negative of the area of a triangle where the base is 2 and the height is 2. So this is negative base times height over 2, or negative 2. So this one actually has a negative value. Another interesting property is what's known as the additive interval property. So if we have f integrable on 3 closed intervals determined by a, b, and c, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. Now, it doesn't matter which order your a, b, and c actually come in on a number line, but what does matter is that this c right here matches with this c right here, and you can use this. And the reason this works, if you want to find the area of this pink region right here, it doesn't really matter if you carve it up and find this area plus this area. It would still be the same. So let's look at an example that uses this. I've got the integral from negative 2 to 2 of the absolute value of x, and the absolute value of x, if you graph it, looks like a V shape, like this. And if we're talking about the lines from x equals negative 2 to x equals positive 2, and the x-axis, you can see that it is positive everywhere, and it kind of forms two different triangles here. So we can make this the integral from negative 2 to 0 of the absolute value of x dx, plus the integral from 0 to 2 of the absolute value of x dx. And we could write this one as the area of a triangle where the base is 2 and the height is 2. And we could also write this one as the area of a triangle where the base is 2 and the height is 2. So this would be base times height over 2 plus base times height over 2, and they happen to be the same. So we get 2 plus 2, or 4, for this definite integral. Some other properties of definite integrals: if you have f and g integrable on a to b and k as a constant, then the functions kf and f plus or minus g are also integrable. You can bring the k out, the constant only. You can split it up into two separate integrals if you want to. So for this one right here, if I'm finding the integral of the absolute value of x plus 2 from negative 2 to 2, I could write this as the integral from negative 2 to 2 of the absolute value of x dx, plus the integral from negative 2 to 2 of 2 dx. Okay. Now from the previous problem, we found out that this first one is 4. But here we're going to have f of x equals 2, so that's a horizontal line. And we're going from -2 to +2. So we're looking at a rectangle. Where the base is 4 and the height is 2. So this is going to be 4 plus 4 times 2, which all adds up to 12. And the last property in this section is what we call preservation of inequality. If f is integrable and non-negative on a closed interval from a to b, then the definite integral from a to b of f of x will also be non-negative. So you're not going to get a negative integral from a or negative definite integral from a positive function. And if f and g are integrable on the closed interval from a to b and f of x is less than or equal to g of x for every x in the interval from a to b, then the integral from a to b of f of x with respect to x will be less than or equal to the integral from a to b of g of x with respect to x. And you can see that illustrated here in this picture. So this is my f and this is my g. So since these are both positive, the definite integral is going to represent the area under the curve, between the curve and the x-axis. So this darker pink area is the integral of f, and you can see that from here all the way down to the x-axis would be the integral of g. So it makes sense that those integrals would be would preserve that inequality. So the integral from a to b of g of x is definitely going to be higher than the integral of f of x because it's got more area under it. So those are some properties of definite integrals. And like I said earlier, in section 4.4, we're going to talk about how definite integrals and indefinite integrals are related to each other.